Okay, so we're moving on to problem 3 here. I have problem 4 down here. We're not doing it in this video. That'll be the next one. But it's kind of got an important part that I think helps answer question 3. So question 3 in chapter 2 says the quadratic and linear force of a moving sphere in a fluid are given by 2.84 and 2.82. Show that the ratio of these two kinds of drag force can be written as F quad over F ln equals R over 48. We talked about R a little bit. And here it says R is D times V times, we have that little, let me highlight it here. And so basically we have to show that F quad over F ln is equal to this. And then for part B, we're going to use that because they give us some numbers to plug in. And don't worry about question 4 yet. Okay, well, the ratio of F quad over F ln, all we have to do is plug in the values they gave us. So F quad's right down here. That's 2.84. So we can say we can just write all that down. And then F linear, we were given in the previous problem, if you guys remember. If not, you can check that one out. Let me write my eta a little bit better. Okay. Now A, D is the sphere's diameter, right? Now A, as we see it here, I think it says it somewhere, but A is the area. Does it mention it here? Maybe it doesn't. But what we do know, A is the area, and A is pi r squared. Or we can say area is pi, the diameter divided by 2 squared. Or is pi d squared over 4. Okay, well, we can plug that in for the A here. So let's just write this all down. So instead of A, we can put pi d squared over 4. I think that makes sense for the most part. Hopefully everyone's okay with that. And then we can write that. Okay, let's see. How can we simplify this? This will just be pi diameter squared times V squared all over what? Okay. Well, actually, there should be a V somewhere down here, I believe. There should be a V here. There we go. So there's a V in the denominator. I forgot about that guy. I was about to say the V squared is a little weird. It just drops to V. Okay. So now we're here. And this actually should be a 12 now because of the 4. And now we can simplify this a little bit because you can see like the pi's cancel, one of the d's cancels. And this is all that we're left with. Well, R is given right there, as you can see right here. So that's going to be important. And then also the fact, I think it's mentioned over here, this K is 1/4 for a sphere. So we can say that is Q dV over, now 12 times 4, that's 48. And then we have our eta. And we know R was given as just this. So then this is just R over 48. So there you go. There's the ratio of the two drag forces. And now for part B. Part B, we want to find R for a steel ball given the diameter and then given the other factors that we have. So the first thing we want to do, we're given the speed. Yeah. Okay, so the first thing we want to do is convert everything. So the diameter is just 2 times 10 to the negative 3 meters. And then the speed is 0.05 meters per second. And then the density, let's see, we have 1.3 grams per centimeter cubed. Let's convert that really quick. We want to convert it, we need kilograms. So that gets rid of the grams. And then 100 centimeters per 1 meter. It's cubed. Let's see, our G's cross, our centimeters cross. Perfect. And then that'll just be 1.3 times 10 to the third kilograms per meter cubed. Okay. So now, since we know what R is equal to, we can substitute all these things in. So we know D, we know V, we know Q, and then I think they mentioned eta as just 12 newtons times seconds per meter squared. So we can plug all that in, and if you plug this in, you should get about 0.01. So really, for part B, all you really have to do is convert and plug in. So not too bad. Hopefully